Imagine peering across 124 light years of empty space and finding a world that just might be whispering to us, "I'm alive." That's the tantalizing possibility that has astronomers buzzing about a distant exoplanet named K2-18b. It's not Earth 2.0, it's not even close really, but it may have something no other world has shown us quite this clearly, a chemical fingerprint that, here on Earth, only life can leave behind. Let's unpack what's got the scientific world leaning forward in their chairs. Astronomers using the James Webb Space Telescope, arguably humanity's most advanced eye on the cosmos, have detected a potential biosignature in the atmosphere of this distant planet. Not a blurry maybe, not a far-off suggestion, but what researchers are calling the most promising sign yet of potential life beyond our solar system. Now, to be clear, no one is popping champagne just yet. The findings are cautious, but they're real, and they're remarkable. Here's what they found. Among the chemical signatures in K2-18b's thick hydrogen-rich atmosphere, scientists detected traces of dimethyl sulfide, DMS, and possibly its chemical cousin, dimethyl disulfide. That might not sound like much until you realize something crucial. On Earth, both of these compounds are produced exclusively by life, specifically by marine phytoplankton. That means if the signal holds up, we could be looking at something unprecedented, a molecule associated only with living organisms, floating in the skies of a planet light years away. But before we let our imagination run too wild, let's rewind for some context. What is K2-18b, and why are scientists so intrigued by it? K2-18b orbits a red dwarf star in the constellation Leo. It's roughly 8.6 times as massive as Earth and about 2.6 times larger in size, what astronomers call a sub-Neptune. But what really sets it apart is where it sits, right smack in the middle of its star's habitable zone. That's the sweet spot, temperature-wise, where liquid water could exist. And that possibility, combined with its atmospheric composition, has led researchers to classify it as a possible Hycean world. The term Hycean comes from combining hydrogen and ocean. In 2021, Cambridge astrophysicist Niku Madhusudan and his team proposed that some planets might be covered in global oceans beneath thick hydrogen-rich atmospheres. Think Earth's oceans, but under a pressure cooker sky. These worlds might not look hospitable to us, but they could be prime real estate for microbial life, especially aquatic life forms like the phytoplankton we just mentioned. The team's earlier observations of K2-18b had hinted at the presence of molecules like methane and carbon dioxide, but this latest round, using the mid-infrared instrument on JWST, brought something new and far more provocative to light. The spectral signature of DMS came through strongly. That's the key detail. It wasn't subtle, and it wasn't buried in noise. It was loud and clear. So, should we be shouting from the rooftops that we've found aliens? Not quite. Even the researchers behind the study are urging caution. Madhusudan himself has emphasized the importance of skepticism. Science, after all, thrives on doubt. The detection has a confidence level of around 3 sigma. For context, a 5 sigma result is typically required before scientists start using words like discovery. 3 sigma means there's about a 0.3% chance the finding is a fluke. Encouraging, sure, but not yet conclusive. More data is needed. The team estimates that somewhere between 16 and 24 additional hours of JWST observation time could push the evidence from intriguing to groundbreaking. That sounds simple enough, but time on JWST is extremely limited and in high demand. Still, the implications are huge, and the astronomy community is paying attention. Astrobiologist Eddie Schwieterman, who has studied K2-18b extensively, shares the excitement but remains grounded. According to his analysis, if DMS really is present in the planet's atmosphere, its production rate would have to be about 20 times greater than what Earth's oceans currently generate. That's a hefty requirement, but not impossible. In some pockets of our oceans, local DMS production can far exceed the global average. The challenge, he says, is figuring out whether any non-biological processes could be creating that much DMS. So far, no convincing explanation has emerged. Then there's another puzzle, the absence of ethane. If DMS and DMDS are breaking apart under the planet's ultraviolet radiation, as they would be, one would expect to find ethane as a byproduct. But so far, there's no clear sign of it. Could our models be wrong? Is the signal misinterpreted? Or are we truly seeing life as we don't yet understand it? Adding another layer of complexity, not everyone agrees on what K2-18b even is. Some researchers think it's a Hycean world, sure, but others propose it could be a hot magma ocean with a hydrogen-rich atmosphere. That would be a profoundly different environment, hellish, molten, and entirely inhospitable to life as we know it. Yet others categorize it as a mini Neptune, with a thick gas envelope and no solid surface at all. That, too, raises questions about where life might form and how it could persist. MIT astrophysicist Sarah Seeger, a giant in the field, has noted that interpretations of this planet vary wildly, and she's not convinced DMS detection means life just yet. Her perspective underscores the challenge here. We're pushing the boundaries of what's observable, and sometimes the excitement can get ahead of the evidence. That said, this isn't just hype. This is real science, unfolding in real time. The detection of DMS, if confirmed, would be a historic moment in our quest to answer one of humanity's oldest questions. Are we alone? It's not proof. It's not even a declaration. But it is a step. Perhaps the biggest step we've ever taken toward that answer. It also opens the door to a much broader conversation. Madhusudan puts it best when he says, the bigger question might not be whether life exists out there, but whether we as a species are ready to find it. Because, let's be honest, life as we don't know it might look nothing like the microbes, plants, or animals we're familiar with. It might exist in forms we can barely imagine, in environments we've long considered inhospitable. If life does exist on K2-18b, it likely lives in a high-pressure, hydrogen-rich soup, possibly beneath global oceans sealed under a heavy sky. That's not our idea of paradise, but it might be someone else's home. This search for life isn't just about scanning the skies for Earth clones. It's about understanding what life truly is. It's about recognizing patterns, spotting anomalies, and asking the right questions. DMS and DMDS may be the start. Tomorrow, it could be something else. A different molecule, a different planet, a different mystery. And that's where we are now, on the edge of a discovery, not quite ready to declare it, but definitely ready to keep looking. Because what if this is it? What if this strange, watery, faraway world is the first whisper of something bigger, something shared? It's easy to forget, in the flood of scientific data and cautious footnotes, just how wild this moment really is. We've built a telescope, launched it into space, pointed it at a tiny point of light, and found something unexpected, something that just might be alive. The search continues, and with every photon collected, every molecule identified, and every hour of telescope time, we step closer to understanding our place in the universe. So, the next time you look up at the night sky, take a moment to consider, one of those stars, barely visible to the naked eye, might be shining down on an ocean-covered world teeming with microscopic life. Not just in theory, not just in dreams, but maybe, just maybe, for real.